and this lecture is over mineral resources. In 2019, protesters from a handful of indigenous Chilean communities created a roadblock to hobble operations for two of the world's top producers of lithium. The lightest metal on Earth, lithium is a coveted commodity because of its use in the manufacturing of glass and ceramics, and more recently, for the production of rechargeable lithium-ion batteries, which are used to power, among other things, electric cars. Soon, researchers hope mega batteries that store excess energy from wind and solar power installations will be available. The promise of rechargeable lithium-ion batteries helping the world transition from fossil fuels to cleaner sources of energy has fueled a rapid increase in lithium mining, and demand is expected to continue to increase. Chile possesses one of the world's largest lithium deposits, found in brine saltwater deposits just beneath the Salar de Atacama, which is a 1,200 square mile expanse in northern Chile's Atacama Desert. Other commercially valuable materials such as copper and potash for fertilizer are also found there. Lithium mining began in Chile in the 1970s and picked up in the 1990s, shortly after lithium-ion batteries hit the market. The mining operation extracts vast quantities of fresh water in addition to salt water withdrawn from the salar, and the area is already among the driest places on Earth. As such, many scientists, as well as local residents, worry that mining is harming the Chilean environment beyond its ability to recover and worsening social inequality in a region that is already economically struggling. As water is depleted and salinity levels increase in the soil, biodiversity could be lost, including microbes that live in the salty water found in the Atacama. Life forms so unique, they give scientists a window into what microbial life, if it exists, might be like on Mars. Villagers also rely on the region's fresh water to graze their animals and grow crops like maize and alfalfa. Without enough, farming could become impossible. But wait a minute, this is cleaner than fossil fuels? Again, I'm very skeptical of the statements that the book is making. If you put it into a business sense, it's almost like the lithium-ion battery industry is competing with the fossil fuel industry, so the industry creates politically charged words and phrases like climate change, global warming, cleaner energy. But is it really? A 2016 study by NASA shows that the Earth's vegetated lands have significantly become greener over the last 35 years due to the rising levels of atmospheric carbon dioxide. To me, that seems like it's cleaner than a mining process that makes it so you can't farm the land anymore. Like I always say, follow the money, and there are a lot of angles to this problem. And that brings us to key concept number 1. Ore minerals are finite resources that provide a wide variety of materials essential to the production of construction materials, electronics, machinery of all kinds, and an array of household products. So chances are, wherever you're hearing this right now, you are surrounded by a variety of different materials: aluminum, copper, lithium, zinc, granite, marble, and so on, derived from mineral resources. Minerals are naturally occurring chemical compounds that exist as solids with predictable three-dimensional repeating structures, or crystals. Their chemical composition and crystalline structure give each mineral distinct physical properties. Most metals and rare elements are bound up with more common elements like oxygen or sulfur in mineral deposits. When these exist in formations from which they can be profitably extracted, they are called ore minerals, or ores. In addition to its presence in the Atacama, dissolved in the brines found there, lithium is found in hard rock ore deposits where it is bound up in minerals such as spodumene and petalite. One class of elements mined from mineral deposits is the rare earth elements, so named not because they are scarce, but because they are not commonly found in concentrated ore deposits. Rare earth elements are a group of chemically similar elements that are finding their way into all kinds of modern products used to, for instance, tint sunglasses, power laptops and cell phones, and put the color into color televisions. Precious metals like gold and silver used in jewelry are also mineral resources. In fact, metals are an essential component of virtually all electronic devices, thanks largely to their malleability and their ability to conduct electricity. So mineral deposits are almost always found as a component of rock, that is, an aggregate of one or more minerals. Rocks can be used as resources themselves, for instance, as building materials like concrete or gravel, or they can be used as sources for specific minerals that are used once these minerals are extracted. Often, rocks contain common non-metallic minerals like quartz and feldspar, the most abundant minerals on Earth. Minerals are almost everywhere in almost everything. So today, our demand for minerals is higher than ever. Annual per capita use of the United States is slightly more than 40,000 pounds of minerals each year. Of this, nearly half goes towards the stone, sand, and gravel used to make roads, buildings, and bridges. Yet many minerals we use go towards things we can't really see. The circuit boards and rechargeable batteries in electronic devices, computers, and cars. Lithium-ion batteries especially are crucial to these products, and the need for lithium, cobalt, nickel, and other components of these batteries is going to increase as electric vehicles become more and more prevalent. But the problem is that extracting minerals from the earth has brought an array of negative consequences. Not just environmental, which would be air and water pollution, but also societal health hazards and human rights violations felt by the Atacama farmers and others around the globe. What's more, demand for all types of resources, from rare earth elements to precious gems to familiar metals like nickel and copper, is rising slowly but steadily as the population continues to climb. Standards of living increase across the globe, and unprecedented technological advances create a litany of new uses for many metal and non-metal mineral resources. The lengths we will go in order to extract the minerals we need are remarkable and sometimes surprising. Who would have thought that we would need to mine salt flats that have been sitting undisturbed in ancient lakes in rural Chile in order to power our electric cars? And this is infographic number 1. We depend on many mineral resources to make the products we use every day. Common minerals you are familiar with, as well as rare ones you may never have heard of, can be found in our homes and household items. This diagram points out some of the minerals you might find in the average dorm room. And that brings us to key concept number 2. Strong geological forces, such as those that power plate tectonics, slowly but constantly reshape the Earth's surface and interior. New minerals are formed at plate boundaries, and the movement of tectonic plates redistributes minerals in the Earth's crust. Minerals include both metals like gold, silver, lithium, and other rare earth elements, and nonmetals like quartz and rock salt, and they are classified according to several physical properties such as hardness and luster that arise from their chemical composition and structure. To make use of minerals, in other words, to find large deposits that we can mine or to design synthetic compounds with similar properties, we must first understand the geological forces that create and concentrate them. The scientific field of geology examines the physical and chemical makeup of Earth and the processes that shaped and continue to shape our planet. Earth is composed of discrete layers of solid rock and liquid metal that differ according to chemical composition and temperature. The Earth's layers get hotter at increasing depths, and at its center is the hottest, densest portion of the Earth, the core, made predominantly of iron. There is a solid inner core as well as a liquid outer core. The uppermost portion is the crust, made up of a thin, relative to the size of the Earth that is, layer of rock. oceanic crust is primarily basalt, whereas the continental crust is largely granite, a rock that usually contains the minerals quartz and feldspar as well as others. The continental crust is thicker than the oceanic crust, but the oceanic crust is denser. Valuable mineral deposits and fossil fuels are found in the crust, and our mines and drilling operations tap these resources. Between the core and the crust is the mantle, which is a region composed of solid rock. The uppermost mantle region is rigid, like the crust, but is composed of different types of rock, primarily peridotite, so it is not considered part of the crust. Together, the crust and this hard upper region of the mantle are known as the lithosphere. This term lithosphere is sometimes used to describe all the rock found on Earth from crust to core. The lithosphere does not exist as one continuous shell around the Earth, but rather it is broken into discrete tectonic plates that fit together like the pieces of a jigsaw puzzle. These plates can consist of continental crust, oceanic crust, or a combination of the two. The mantle region directly below the lithosphere is called the asthenosphere. The asthenosphere is so hot that the peridotite rock begins to soften and becomes more malleable like putty or molding clay, allowing it to flow slowly. This is called plastic behavior. That is the ability to deform without breaking. Though softer than the peridotite of the upper mantle, rock in the asthenosphere is not molten or liquid rock. It is still considered a solid. However, this layer is the source of magma, molten rock, that forms in locations where the temperature rises or pressure is lowered, or both physical conditions that begin to melt the rock. The asthenosphere is in motion due to convection, that is, rock deeper in this part of the mantle is hotter and less dense than rock above, so it flows upward. Cooler rock flows downward as it is displaced by the upward flowing hotter rock, which cools as it rises and then sinks again. This creates a convection cell, or the cyclical movement of a hot and cold substance that keeps the asthenosphere moving. This convection is powered by heat produced deep within the Earth from the decay of radioactive material and by residual heat remaining from the formation of the planet. The tectonic plates that sit on the asthenosphere move very slowly, about 0.5 to 6 inches per year. Your fingernails grow at similar rates. The continents that ride on these plates have taken up different positions on the planet in the past. At least twice in the Earth's history have come to form a single supercontinent. Earthquakes and volcanoes can give scientists clues about the locations of plate boundaries, that is, areas where two or more plates meet, because they occur in regions where plates move relative to one another. The energy released at plate boundaries fuels volcanic and hydrothermal activity that end up creating new minerals and redistributing others within the Earth's crust. So geologists recognize different types of plate boundaries. Plates approach each other at convergent plate boundaries. Where they meet, the denser oceanic plate will subduct or slide under the other, forming an ocean trench. If two oceanic plates converge, the older, denser plate will subduct. It is in this action that the movement of the tectonic plates is fueled. As gravity pulls the denser plate deeper into the mantle, the rest of the plate is dragged along behind it. Volcanic activity is seen in subduction zones. Magma forms in these areas and then rises to create volcanic mountains or island chains. It is in these areas that rich veins of metal can be found, delivered to the plate boundary by rising magma. This is the case with Chile's Atacama region, where localized volcanic activity fuels the accumulation of lithium in its salts. Similar deposits are found in salt flats in neighboring Bolivia and Argentina, whose salars share a geological history with Atacama. The Salar de Uyuni in Bolivia is the largest salt flat in the world and may be the world's largest source of lithium. The region known as the Lithium Triangle holds an estimated 70% of the world's lithium. When two continental plates collide, subduction does not occur because their density is less than that of the mantle below, so they will not stick into the mantle. Rather, they crash into each other in slow motion, collisions that cause the lithosphere to bend and buckle, reforming the face of the Earth. This is the power that fuels mountain building. As with other plate boundaries, earthquake activity is seen at convergent plate boundaries as well. Plates move apart at divergent plate boundaries. At these boundaries, magma travels upward from the asthenosphere through the fissure formed as the plates diverge and cools, creating new crust. This new crust takes the form of underwater ridges at oceanic divergent plate boundaries, for example, the Mid-Atlantic Ridge, or becomes the floor of a rift valley if divergence occurs on a continent. Many important metallic minerals are formed at these ridges and can be mined. And that brings us to a third type of plate boundary that exists, a transform plate boundary, where two adjacent plates slide past each other laterally or parallel to the boundary, one in one direction and the other in the opposite direction. These regions are often the sites of earthquakes that are created when plates slide to release the buildup of tension. The crust may be cracked or broken apart after this movement, but no new crust is created and no crust is destroyed. Most transform plate boundaries are in the oceans, but the San Andreas Fault that runs through California is an exception to that. Plate tectonics is a powerful unifying theory of geology that explains the dynamic processes that shape and reshape the face of the Earth. As plates move, they cause earthquakes, create mountain and volcanoes, and form trenches or depressions at the plate boundaries. Powerful forces form and move mineral resources around, often concentrating them at plate boundaries. We mine these regions of the lithosphere, both on land and at sea, to retrieve the valuable minerals and ores they contain. But we also must endure the hazards created by these forces, destructive events that can overwhelm even our best attempts to be prepared. And that brings us to infographic number 2. Earth is composed of discrete layers. The crust, mantle, and core are distinguished by their distinct chemical compositions. Furthermore, regions within these layers that have different physical properties are also recognized. Mineral and fossil fuel deposits are found in the Earth's crust. Moving on, powerful geological forces are constantly but slowly rearranging the face of the Earth. The lithosphere is made up of tectonic plates that move slowly, powered by the deep heat within the Earth. And that brings us to key concept number 3. Geological forces contribute to destructive events such as earthquakes, landslides, tsunamis, and volcanic eruptions. So on May 22, 1960, Chile was devastated by a magnitude 9.5 earthquake. That is a sudden shaking of the ground, most commonly caused by tectonic plates moving relative to each other or volcanic activity. It was the strongest earthquake ever measured. In 1994, Bolivia was shaken by a massive magnitude 8.2 earthquake that was felt as far away as Toronto, Canada. There was also a magnitude 6.1 earthquake that hit Argentina on January 4, 2020. The fact that such lithium-rich countries are also at risk for earthquakes is no coincidence. The regions of the Earth that are the richest in minerals tend to be the most at risk for geological hazards because both are created by the same strong geological forces. Earthquakes occur at faults, that is, underground regions where cracks are found in the lithosphere. Plate boundaries are faults, but so are cracks occurring within a single plate. Rocks on either side of these faults typically move slowly, but if friction keeps them static for a period of time, stress builds up from accumulating pressure. When the energy from this stress is suddenly released, it moves through the ground in the form of seismic waves, causing the ground to shake. This energy disperses from what is called the earthquake's focus, that is the underground location where the earthquake originated, to the epicenter, that is the point directly above the focus on the Earth's surface. The epicenter is typically where the most damage from an earthquake occurs, but damage can occur for miles around the epicenter too. And that is going to depend on the earthquake's strength. That said, most earthquakes are hardly felt and cause little to no damage. The damage done by an earthquake is shaped by its depth, by the nature of the geological materials through which the seismic waves travel. Shrinking is greater in less consolidated materials such as silt or sand compared to waves that pass through rock, and by what has been built above the ground near the epicenter. If buildings and other structures are constructed to withstand earthquakes, damage is often minimized. The deadliest earthquake in recorded history happened in 1556 in China. It was a magnitude 8.0 earthquake, less than the one that hit Bolivia in 1994, yet it killed approximately 830,000 people, many of whom lived in cave settlements that collapsed. The second most fatal earthquake was the magnitude 7 earthquake that struck Haiti in 2010. This earthquake was so deadly, perhaps as many as 316,000 deaths by one estimate, because it occurred close to a populated area with buildings poorly equipped to handle the shaking. Earthquakes can also be caused by human activities such as deep drilling for geothermal power plants, the use of injection wells to dispose of fracking fluid, and even damming up rivers and flooding river valleys. The extra weight of the water in a reservoir behind a dam can trigger earthquakes in seismically active areas. Volcanoes are another geological hazard. They form when magma works its way up from the asthenosphere, exiting the volcano as lava. When lava and erupted ash cool, they harden into rock that forms the conical volcano shape. Like earthquakes, most volcanoes form near plate boundaries. They're found at divergent boundaries where the plates are spreading apart, as well as near subduction zones at convergent boundaries. The region where the Pacific Plate meets its adjacent plates is known as the Ring of Fire, a seismically active area encircling much of the Pacific Ocean, where 90% of earthquake activity occurs and 75% of volcanoes are found. Argentina and Bolivia are close to the Ring of Fire, which extends up the western coast of South America. Chile sits directly along it and has as many as 2,000 active and inactive volcanoes. Also, as an active earthquake zone, it is not unusual for Chile to experience more than 100 earthquakes in a month's time. Volcanoes can also form away from plate boundaries where hot spots bring high heat close to the crust. The Hawaiian Islands in the middle of the Pacific Plate formed one after the other as the plate drifted over just such a hot spot. Because hot spots remain stationary while the plate slides past, an evaluation of hotspot island chains helps geologists to reconstruct past rates and the direction of tectonic plate movement. Volcanic eruptions can be explosive and extremely dangerous. The eruption of Mount Vesuvius in Italy in 79 AD buried the Italian town of Pompeii, killing more than 20,000 people. Sometimes earthquakes and volcanic eruptions happen at the same time or one after the other. In March 1980, scientists noticed a sudden increase in earthquake activity in the Cascade Mountain Range around Mount St. Helens in southern Washington state, with as many as 3 earthquakes happening each hour. Shortly thereafter, Mount St. Helens erupted, forming a crater on the top. It soon became clear that magma was rising within the volcano and pressure was building up inside. A visible bulge appeared near the top of the mountain and grew outward as much as 6 feet per day. On May 18, 1980, the volcano erupted again, this time with massive force, blowing off the side of the mountain. Superheated gas and rock blew out of the volcano in a blast that created the largest landslide in recorded history. So when unstable soil suddenly gives way on a slope, landslides, another geological hazard, can occur. They often happen after earthquakes, when material is washed away during rainstorms or when soil becomes heavily saturated with water, such as after a heavy rainfall. Landslides can also develop due to an excess weight of snow, as well as after eroded riverbanks, dikes, or coastal areas collapse. When earthquakes or landslides occur under the ocean, they create tsunamis. Sometimes tsunamis are mistakenly called tidal waves, but they are not caused by the tides. When the seafloor suddenly moves during an earthquake, the energy is transferred to the water, creating waves that ripple out and can travel for miles. In the open ocean, these waves look like large swells, not towering waves, but as they approach land, water piles up behind the waves, making them extremely tall. After an underwater earthquake shook Japan in 2011, a powerful tsunami came ashore. It killed close to 20,000 people and inundated the nuclear power facility at Fukushima, and this caused a meltdown at the nuclear facility. And that brings us to infographic number 3. Earthquakes and volcanic activity are most often found above divergent and convergent plate boundaries. The Ring of Fire represents the area where the Pacific Plate meets surrounding tectonic plates, forming an almost continuous series of trenches and volcanoes. This seismically active area accounts for the majority of earthquakes and volcanic activity on Earth. And that brings us to key concept number 4. Rocks are formed and transformed by melting, cooling, erosion and deposition, and pressure. So it is through the internal processes described in the earlier sections, that is through the movement of tectonic plates and the resulting release of energy, that many minerals are created. Under extraordinary heat and pressure, atoms of naturally occurring elements combine to form new minerals, many of which are stable enough to endure for long periods of time. The relative abundance of elements in any given location determines which chemical reactions will be favored and thus which minerals will form. Because of this, minerals are not distributed evenly throughout the planet's lithosphere. Different minerals are abundant or uncommon in different parts of the Earth. But it is not just internal forces that influence the Earth's geology. While internal forces can create mountain ranges, external forces like wind and rain wear them back down. Weathering is the breakdown of rock by physical or chemical means. Erosion is the movement of this broken material to another location. This reshapes the Earth's surface from soil in conjunction with the process of biological decomposition and redistribute it, bury, or uncover mineral deposits. As mentioned earlier, most minerals are found alone or in combination as a component of rock, an aggregate of one or more minerals. Rocks, the most common material found on Earth, occur in a variety of configurations, and they are categorized by how they are formed. In fact, rocks are constantly formed and transformed from one type to another via the rock cycle. So igneous rocks form where magma rises and cools at plate boundaries. They are made of silicate minerals, that is, those that contain silicon, oxygen, and other elements. The magma that forms them can cool slowly and crystallize while still underground, forming intrusive igneous rocks such as granite. Pegmatite, a type of rock mined for lithium, is an intrusive igneous rock. When magma exits the ground in a volcanic eruption, it cools and crystallizes quickly, forming extensive igneous rocks above ground, such as basalt or obsidian. So all types of rock can be weathered by physical or chemical means to produce sediments. Erosion transports these rock particles, such as sand and silt, as well as other materials such as shells and organic detritus, to locations where they pile up on top of each other in rivers, streams, and deep basins under the sea. When these sediments accumulate and become compacted, sedimentary rocks are created. Sedimentary rocks can form through one of three processes. In elastic sedimentation, eroded rock sediments accumulate, get compacted by pressure from above, and are cemented together by dissolved minerals in between the clasts. A clast is a fragment or chunk of rock broken down by weathering. This is how shale is made from tiny clay particles and how sandstone is made from sand. Conglomerates and breccias are also classic sedimentary rocks, even though the sediments they contain can vary from small pebbles to large boulders. Classic rock formations may also contain fossil fuel deposits. In biogenic sedimentation, the sediments are biological in origin. Living organisms extract materials from water to form structures such as shells and bones, which, after death, accumulate on lake and seafloors and get compressed over time. Clastic and biogenic sedimentation happen in similar ways. The difference lies in the source material. Limestone and chalk are biogenic sedimentary rocks. They are formed by the accretion and compaction of shells and exoskeletons of marine organisms over time. These rocks can be a window into the geological and biological history of an area, containing fossils that provide clues about climatic conditions of the area at the time they were formed. The third way to form sedimentary rock is through chemical sedimentation. That is when rock forms from concentrated solutes or material dissolved in a liquid that precipitate out of solution. Some limestones form by direct precipitation of calcium carbonate on the seafloor. Salt flats such as Salar de Atacama are evaporate deposits that form via chemical sedimentation in areas where no outlet for water exists. Water that collects from precipitation does not flow away. It evaporates and leaves behind dried salt deposits or concentrated solutions of dissolved materials. Metamorphic rocks are those that have been altered from their original solid rock state by the pressure exerted by moving plates and from deep burial, which heats them enough to cause a physical change, but not enough to melt them and form igneous rock. Being buried deep, these rocks are put under extraordinary amounts of pressure that can slowly transform them. The mineral crystals in the rock may change their orientation or recrystallize to form larger crystals. For example, the metamorphic rock marble is formed when limestone is exposed to sufficient heat to cause the calcium carbonate molecules to recrystallize. Metamorphic rock forms distinctive combinations of minerals under different conditions by analyzing these rocks. Geologists can tell us much about local conditions at the time of formation, allowing them to determine the geological past of an area. And that brings us to infographic number 4. Rocks form and are transformed when they are subjected to high heat and pressure underground and when they are exposed to wind and water on the Earth's surface. And that brings us to key concept number 5. Minerals are mined in both high-tech and low-tech ways, depending on the location, depth, and type of deposit. After mineral resources are extracted, additional processing steps are often needed. So minerals are the building blocks of rocks, but not all rocks contain economically accessible deposits of useful minerals. As mentioned earlier, ores are rock deposits that contain economically valuable amounts of metal-bearing minerals. This means that the minerals within not only have practical applications, but also are concentrated enough to be worth the effort of mining and extracting them. Minerals are considered non-renewable resources. Yes, they form naturally through the aforementioned earth processes, but these processes are extremely slow relative to human lifespans, And for most minerals, we are using up existing deposits faster than new ones are being created. As with many of Earth's resources, the vast majority of mineral use has occurred in recent decades. In fact, of all the minerals used in the 20th century, more than half were used between 1975 and 2000. Also, according to one recent study, only 2.5% of all the copper ever mined was used before 1900. Well, sure, of course, the technology has changed since prior to 1900, and also our mining techniques have become more sophisticated. Mining begins with geologists exploring various rock formations to pinpoint mining-worthy deposits. A mineral resource is a deposit with reasonable prospects for eventual economic extraction, but mining efforts are generally restricted to mineral reserves, those deposits that are economically and technically feasible to tap. Mineral exploration is a science in itself, and one that requires remote sensing, exploratory digging or drilling, and chemical testing to evaluate samples. Once a suitable deposit is located, minerals are extracted using one of several mining techniques. In subsurface mining, the deposits are found deep underground rather than close to the Earth's surface. Zinc, silver, gold, uranium, lead, diamonds, salt, and coal are mined this way. In order to reach these deep deposits, workers create a vertical mine shaft down to the ore deposit. Once the deposit is reached, they create horizontal tunnels that follow the ore vein, the distinct region within the rock that contains a mineral or ore or a coal seam. Elevators and vehicles transport workers deep into the mine. In the room and pillar mining method, enough rock is left behind as pillars support the roof of the mine, and the ore is then removed. After the ore has been taken, the furthermost pillars can be removed, allowing the tunnel to collapse a little at a time behind the retreating miners. In mountainous regions, a sloping shaft rather than a vertical shaft is sometimes made to access the veins. In developed countries like the United States, or in mines that have a lot of financial backing in less developed countries, modern mechanized equipment is used to extract the ore. Subsurface mining is typically more expensive than surface mining, in part because the deep mines have to be ventilated to bring oxygen to the workers and because the mines sometimes get so hot that air conditioning is necessary. In less developed countries, miners still use hand tools such as picks and shovels. In many instances, mining operations in these locations are extremely hazardous, and resulting accidents can lead to human fatalities. So in solution mining, the desired mineral is found in a natural liquid deposit, like the lithium salts found in Chile's salars, which are essentially ancient underground lakes. When a solid deposit contains material that is easily dissolved in a liquid, such as water or acid, a borehole is drilled into the deposit to create an injection well through which the dissolving liquid is pumped. Then the mineral-laden liquid is pumped out through a recovery well drilled into the same formation. When the underground deposit is already dissolved in water, as is the case for lithium, it simply is pumped out. And that brings us to surface mining, which is used when deposits are found close to the Earth's surface. If the deposit is on fairly level ground, strip mining can be done, which involves using explosives and heavy machinery to remove soil and rock above the deposit, called the overburden, in strips, and then removing the mineral resource. In each subsequent strip, the overburden goes on the top of previously mined strips. Strip mines are used to extract fossil fuels such as coal, as well as the oil found in tar sands. So a variation of surface mining known as mountaintop removal is used in the central and southern Appalachian Mountains, where coal deposits are found close to the surface in mountainous areas. The overlying soil and rock are removed to reach the coal seams below, but because the area is mountainous and not flat, there is no place to store the overburden, so it is dumped down the side of the mountain into the valley below, which can be extremely environmentally damaging. When the top of a fairly deep mineral deposit is found close to the surface and the mineral is evenly dispersed throughout the deposit, open pit mining is the method of choice. In this process, heavy machinery and explosives are used to remove the overburden and then the mineral ore. The pit is excavated in terraces or benches to reduce the distance that falling rocks can travel, and this is for safety reasons. These pits can be huge. Rain and groundwater can collect in the crater, so this water must be removed by drilling drainage holes or pumping it out. Copper, iron, gold, uranium, aluminum, diamonds, and stones like granite, quartzite, and marble are mined this way, as are lithium-containing deposits of pegmatite. Quarrying is open-pit mining for materials such as sand, gravel, chalk, and slate. When minerals are dispersed in sediments such as riverbeds that contain heavy minerals or metals, placer mining is used. The material is suspended in water, and the heavy mineral or metal falls to the bottom while the lighter sediments can be washed away. A sluice, which is a trowel that allows the lighter sediments to flow away while the heavier ones fall, is often used for separation. Panning for gold is an example of placer mining that is still used today, but more modern methods are available. These include dredging. Dredging is when a machine is positioned in the water and it excavates the sediment from the riverbed via suction or mechanical dragging and then sends it through a sluice, and hydraulic blasting, in which a strong jet of water is fired at sediments and the slurry is then sent through the sluice. Digging out the ore is just the first step. The ore must be processed to yield a useful form of the mineral. At large-scale ore processing facilities, this includes heavy machinery, some that crush the ore and others that grind it to a fine powder. The mineral may also need to be heated to high enough temperatures and then mixed with other chemicals that bind to the mineral. This is called smelting. This frees it up from the crushed rock. Hazardous substances found in the ore can be released in this process. This contributes to acid rain or toxic air pollution. After smelting, the material is then typically sent through an additional purification step or steps to extract the metal of interest. Electrolysis is sometimes used to extract metals put in solution during the refining process. In this process, an electric current is passed through aluminum oxide, for instance, to extract pure aluminum. Smelting is also used to combine metals to form alloys like steel, which is formed when iron is combined with small amounts of carbon. The processing of lithium brines is done with lower-tech methods. After being pumped to the surface, the briny water is kept in holding ponds to allow the sun's rays to evaporate the water, leaving behind a concentrated solution of lithium and other salts. This process can take 1 to 2 years. After this, the concentrate is delivered to another facility where it is further processed to produce lithium carbonate or lithium hydroxide, the compounds used by industry in the manufacturing of lithium-ion batteries. And that brings us to infographic number 5. A variety of mining techniques are available to access mineral resources. The nature of the deposit, the depth, geometry, concentration, type of ore, etc., influences the type of mining that will be done. Modern mining depends on heavy equipment and can move tremendous amounts of material in search of the desired mineral. This cartoon shows us an example of open-pit mining. Open-pit mining is used when the top of a deep ore deposit is found close to the surface. A wide variety of minerals are mined this way, including aluminum, copper, and diamonds. This is also the method of mining used for hard rock lithium deposits. And that brings us to placer mining. This is used when sediments contain heavy minerals or metals that will easily settle out when mixed with water. Some operations, like this Mali gold mine, still depend on traditional mining methods. And that brings us to key concept number 6. Mining and processing of mineral resources can require high energy and water inputs. Additional environmental impacts of mining include the production of hazardous wastes, habitat destruction, and air, water, and soil pollution. Societal impacts include health problems for miners and community members, the use of child labor, and outright violence. So the same sequence used at large mining operations, that is search, discover, dig, extract, process, plays out at smaller scale mines around the world where impoverished individuals use rudimentary tools and simpler strategies to achieve the same ends. These are known as artisanal mines in order to distinguish them from industrial mines. Similar processing steps are used by artisanal miners, but often without safety protocols to protect themselves or their surroundings from the hazardous materials used or created. As demand for mineral resources has grown and prices have increased in tandem, large-scale operations have come to dominate the landscape. Such mechanization has increased mine productivity by an order of magnitude, mostly by enabling us to access previously unreachable deposits or to reopen shuttered mines. But it has also increased the carbon footprint of mining and the amount of waste produced, and in doing so has amplified the environmental and health consequences that mineral mining and processing bring with them. In addition, large industrial mines often require that vast swaths of land be stripped bare and require the construction of an extensive web of roads for access and transport, both of which can cause serious habitat damage. These combined forces, deforestation and road building, contribute both to soil erosion and water pollution as disturbed topsoil washes into nearby streams. Mining the salt flats of South America also destroys habitat. By pumping out both lithium-rich salt water, around 320 million gallons per week, and removing fresh water from even deeper regions to support the mining operation, mining efforts in the salars of the Atacama Desert of Chile have altered habitat and are adversely affecting nearby residents in this place known as the driest non-polar desert on Earth. Water extraction has been linked to a decline in vegetation and soil moisture, high daytime temperatures, and an increase in drought conditions. The negative effects of mineral extraction aren't restricted to mining. Each processing step produces finely ground rock waste known as mine tailings, some of which may be hazardous. These tailings can contain the hazardous chemicals used or produced during the processing and may be radioactive if the rock formation contain radioactive material. Water traveling through underground mines or above ground piles of waste rock and mine tailings can collect all sorts of contaminants such as heavy metals like mercury and arsenic that are detrimental to human health. In addition, when sulfur-containing rocks at mining sites are exposed to water and oxygen, sulfuric acid forms. This acid lowers the water's pH and produces acid mine drainage that in turn pollutes surface water and groundwater and harms aquatic ecosystems. The now closed Richmond mine in Northern California still releases acidic water into local bodies of water, including the Sacramento River and the Keswick River. The water draining out of the mine has a pH similar to stomach acid, around 1.5. This is acidic enough to kill local fish and other wildlife. There are two basic approaches to address acid mine drainage. One is to prevent its formation or reduce its impact after the formation. Preventing the formation of sulfuric acid in waste rock piles can be accomplished by burying mine tailings or immersing them in water to exclude oxygen needed for the chemical reaction that forms the acid. If acid mine drainage does occur, there are treatment protocols. that aim to neutralize acid through the addition of buffering compounds such as calcium carbonate. Crushed limestone is also commonly used. Indeed, it is nearly impossible to dig so much and so deeply into the earth without affecting the environment. Blasting, digging, crushing, and grinding all create dust, which pollutes the air with small particles of toxic substances and in some cases contains radioactive material. Large mining operations have developed a range of strategies to reduce this dust. They use huge amounts of water when crushing and grinding ore, and they store lightweight waste tailings in ponds, adding to the high water footprint of the operation to keep it from floating through the air. But these solutions bring their own set of environmental problems, such as they generate thousands of gallons of hazardous waste for every ton of minerals mined. And because that waste is so concentrated, the threat posed by a single spill or leak can be significant. Furthermore, the thread between mining and violence spans the globe and involves a range of minerals. For example, independent diamond miners in Zimbabwe have been assaulted and threatened by security guards working for larger-scale mines whose operators want to maintain a monopoly on the region's treasures. That also happens close to home. The Harlan County War was a series of coal industry skirmishes, executions, bombings, and strikes that took place in Harlan County, Kentucky during the 1930s. Perhaps the most disturbing human rights violations is the fact that some mining companies routinely violate child labor laws. For example, the International Labor Organization reports that tens of thousands of children work in gold mines. Other children do backbreaking work in artisanal cobalt mines in the Democratic Republic of Congo. Cobalt makes up the cathode in many rechargeable lithium-ion batteries, and demand for it is through the roof. In December 2019, Congolese families launched a landmark legal class action suit against Apple, Dell, Microsoft, and Tesla, claiming that their children were killed or hurt while mining for the cobalt to make their tech companies' products. Even for adults, mining work can be dangerous. Underground mines collapse or develop pockets of methane that cause explosions or gather high concentrations of other hazardous inhalants, leading them to lung disorders and other illnesses such as black lung disease and ailments suffered by coal miners. And the hazards don't end where the ore is brought to the surface. Toxic chemicals used in processing can pollute the environment even when protective regulations are followed, but this pollution can reach extreme levels when artisanal miners employ the same range of toxic chemicals used in industrial mining, such as mercury and cyanide chiefly among them, in their own crude smelting processes, but without safeguards employed at the industrial level. Artisanal gold miners may use their bare hands to mix crushed ore with mercury. Mercury concentrations in the air inside of such artisanal shops are known to reach 1,000 times the World Health Organization limit for exposure. And that brings us to infographic number 6. Because so much earth and rock are dug up and moved, mining produces unavoidable environmental impacts. Though they may not be the norm, human rights violations such as displacement, violence, and child labor also occur at some mines. And that brings us to key concept number 7. The impacts associated with mineral use can be reduced by using safer mining and processing techniques, implementing more efficient manufacturing processes to reduce waste or the volume of material needed, recycling minerals, and extending the life of mineral-containing products. So we are always going to need mining in order to meet the growing needs of our modern society. Unfortunately, in nations across the globe, regulations often fall short of protecting the environment and surrounding communities from the negative impacts of mining. In the United States, mineral mining on federal land is still largely governed by the General Mining Act of 1872, which was put into place to protect miners and their claims and encourage Western settlement. More recent mining laws uphold the goal of fostering the domestic mineral industry too. This law allowed a miner or a group to stake a claim on any public land open to mining and to purchase the mineral rights for as little as $2.50 per acre. Though claim holders must pay a nominal annual maintenance fee from $155 to $165 depending on the type of claim, they do not have to pay royalties on any mining income to the government. Much of the oversight of mining occurs at the state level. Federal mining laws still tend to focus on protecting the rights of miners rather than environmental protections. This has resulted in serious environmental damage in the United States, especially west of the Mississippi River. The mining industry does not have to abide by rules set forth by the Mine Safety and Health Administration to protect its workers. However, at the federal level, environmental protection from mining operations largely falls under other laws that might become relevant, such as the Clean Water Act and the Endangered Species Act. Federal law does mandate that some closed and abandoned mines undergo reclamation, that is, the process of restoring a damaged natural area to a less damaged state. In many cases, the responsible parties can't be found or can't pay for reclamation, but when they are identified, and they are expected to cover these costs. Closed coal mines, for instance, have to be reclaimed according to the Surface Mining Control and Reclamation Act of 1977, but hard rock miners, which are mined for mineral ores and metals in hard rock deposits as opposed to soft rock deposits such as those that contain coal, do not have such a mandate. On several occasions, Congress has introduced legislation to update the General Mining Act of 1872, but little progress has been made. The Hard Rock Mining and Reclamation Act, for instance, introduced several times since 2007, would require that hard rock mining operations pay the government royalties on the minerals they extract and also pay a fee based on the amount of material they mine toward a reclamation fund, but this law has yet to be passed. If there is a silver lining to the story of mineral resources that fuel modern life, resources that we dig into the earth to access and fight and even die over, it is this: many are eminently reusable. In fact, the greatest reserves yet of gold, silver, and lithium may not be hidden in some desert canyon, but sitting in the backs of our own closets and garages or scattered throughout our landfills as e-waste, electronic waste. An average gold mine produces a mere 5 grams of gold per metric ton of rock, and sometimes less, depending on the ore being mined. A metric ton of cell phones, on the other hand, might contain nearly 200 grams of gold, plus over 100 kilograms of copper, 3 grams of silver, 1.2 kilograms of lithium, and a smattering of neodymium and other rare earth elements. Likewise, for our flat-screen televisions, laptops, and tablets, they all contain a bevy of essential and non-renewable mineral resources. By recycling these products, we can reclaim these metals so that they can be used again. E-waste, in fact, may become the main source of many of the rare earth elements used to manufacture electronics as ground reserves become depleted. Metal recycling is already big business in the United States and elsewhere. Indeed, the process of recycling scrap metal from vehicles and home appliances has long been an industry unto itself. And aluminum, the most recycled metal on Earth, is so effectively recycled in the United States that on average, the aluminum in any given beverage can is back on the shelf within 2 months as another can. It's clear from such successes that recycling can supply some of society's needed minerals and in doing so reduce the amount of ore minerals that must be mined. But for that to work, recycling must be done properly. And when it comes to e-waste, we don't yet have a widely available recycling program. Most of our discarded cell phones, computers, and flat-screen televisions collect dust in the crevices of our homes and offices or are discarded with the trash. Even when sent to recyclers, electronics may end up in poorly managed operations in a developing country where low-paid workers labor to extract the various metals contained within the equipment. The simple tools and methods used often expose workers to significant health hazards and contaminate the local environment. So far, the world has generated more than 45 million tons of e-waste, but only 20% is being safely recycled. There is, of course, a better way. Programs similar to the ones we have for plastic recycling, but focused on e-waste, could make a huge difference. In other parts of the developed world, an entire industry is being born around this very idea. The growing demand and rising price for elements like gold and neodymium have made recovering them from hybrid vehicles, electronics, and other products an attractive endeavor, one that several big-name producers such as Honda, Toyota, and Hitachi are pursuing. With the ever-increasing growth in the cell phone market and the push toward electric vehicles, both of which rely on lithium-ion batteries, the need to reclaim and recycle lithium, cobalt, and other valuable materials from e-waste rises every day. This will not only help meet lithium and cobalt needs, but also reduce the environmental damage that comes from mining and processing of these materials. Thanks to new technology that has made extracting metals from electronics easier and cheaper, Japan has already opened several recycling plants devoted to electronics. France is also quickly following suit. Recycling, while valuable, should be coupled with other conservation efforts. After all, it is only one of the 4 R's. The other 3, refusing, reducing, and reusing, could serve us well here. Many experts agree that neither recycling nor scientific advances will replace all that we dig from the earth. Indeed, mining will be necessary for many lifetimes to come. And that brings us to infographic number 7. Recycling metal products to recover the metals for reuse extends their useful life and reduces the need to obtain the metals from mined ores, decreasing the environmental and health impacts associated with mining and processing the ore. This slide shows a comparison of the 2 methods for obtaining aluminum to make a new aluminum can. One is the production from the raw material bauxite ore, or the other from recycled aluminum cans. This highlights the differences between these 2 processes, especially with regard to energy savings. And that brings us to our core message. Modern society depends on mineral resources. Extracting and processing mineral resources can lead to environmental damage, occupational hazards, and negative impacts on local communities. Some mineral resources are becoming scarce, and sustainable use is critical. So let's summarize our chapter. Modern society is dependent on mineral resources for all kinds of products and industrial processes. Minerals are found in rocks that are formed through the rock cycle. Minerals are not evenly dispersed around the planet, and their extraction can lead to conflict and human suffering. Recycling, refusing, reducing, reusing, and redesigning are important steps in reducing our dependence on mining.